Arithmetic or arithmetics is the oldest and most elementary branch of mathematics. It consists of the study of numbers, especially the properties of the traditional operations between them: addition, subtraction, multiplication and division. Arithmetic is an elementary part of number theory, and number theory is considered to be one of the top-level divisions of modern mathematics, along with algebra, geometry, and analysis. The terms arithmetic and higher arithmetic were used until the beginning of the 20th century as synonyms for number theory and are sometimes still used to refer to a wider part of number theory. History. The prehistory of arithmetic is limited to a small number of artifacts which may indicate the conception of addition and subtraction, the best known being the Ishango bone from Central Africa, dating from somewhere between 20,000 and 18,000 BC, although its interpretation is disputed. The earliest written records indicate the Egyptians and Babylonians used all the elementary arithmetic operations as early as 2000 BC. These artifacts do not always reveal the specific process used for solving problems, but the characteristics of the particular numeral system strongly influence the complexity of the methods. The hieroglyphic system for Egyptian numerals, like the later Roman numerals, descended from tally marks used for counting. In both cases, this origin resulted in values that used a decimal base but did not include positional notation. Complex calculations with Roman numerals required the assistance of a counting board or the Roman abacus to obtain the results. Early number systems that included positional notation were not decimal, including the sexagesimal system for Babylonian numerals and the vigesimal system that defined Maya numerals. Because of this place value concept, the ability to reuse the same digits for different values contributed to simpler and more efficient methods of calculation. The continuous historical development of modern arithmetic starts with the Hellenistic civilization of ancient Greece. Although it originated much later than the Babylonian and Egyptian examples. Prior to the works of Euclid around 300 BC, Greek studies in mathematics overlapped with philosophical and mystical beliefs. For example, Nicomachus summarized the viewpoint of the earlier Pythagorean approach to numbers, and their relationships to each other, in his Introduction to Arithmetic. Greek numerals were used by Archimedes, Diophantus and others in a positional notation not very different from ours. Because the ancient Greeks lacked a symbol for zero, they used three separate sets of symbols. One set for the units place, one for the tens place, and one for the hundreds. Then for the thousands place they would reuse the symbols for the units place, and so on. Their addition algorithm was identical to ours, and their multiplication algorithm was only very slightly different. Their long division algorithm was the same, and the square root algorithm that was once taught in school was known to Archimedes, who may have invented it. He preferred it to Hero's method of successive approximation because, once computed, a digit doesn't change, and the square roots are perfect squares, such as 7,485,696, terminate immediately as 2,736. For numbers with a fractional part, such as 546.934, they used negative powers of 60 instead of negative powers of 10 for the fractional part 0.934. The ancient Chinese used a similar positional notation. Because they also lacked a symbol for zero, they had one set of symbols for the units place, and a second set for the tens place. For the hundreds place they then reused the symbols for the units place, and so on. Their symbols were based on the ancient counting rods. It is a complicated question to determine exactly when the Chinese started calculating with positional representation, but it was definitely before 400 BC. The Bishop of Syria, Severus Sabokht, Indians possess a method of calculation that no word can praise enough. their rational system of mathematics, or of their method of calculation. I mean the system using 9 symbols. Leonardo of Pisa in 1200 AD wrote in Liber Abaci, "The method of the Indians surpasses any known method to compute. It's a marvelous method. They do their computations using 9 figures and symbol 0. The gradual development of Hindu Arabic numerals independently devised the place value concept and positional notation, which combined the simpler methods for computations with a decimal base and the use of a digit representing 0. This allowed the system to consistently represent both large and small integers. This approach eventually replaced all other systems." In the early 6th century AD, the Indian mathematician Aryabhata incorporated an existing version of this system in his work, and experimented with different notations. In the 7th century, Brahmagupta established the use of 0 as a separate number and determined the results for multiplication, division, addition and subtraction of 0 and all other numbers, except for the result of division by 0. His contemporary, the Syriac bishop Severus Sabox, described the excellence of this system as valuable methods of calculation which surpassed description. The Arabs also learned this new method and called it Hesab. Although the Codex Vigilanus described an early form of Arabic numerals by 976 AD, Fibonacci was primarily responsible for spreading their use throughout Europe after the publication of his book Liber Abaci in 1202. He considered the significance of this new representation of numbers, which he styled the method of the Indians, so fundamental that all related mathematical foundations. In the Middle Ages, arithmetic was one of the 7 liberal arts taught in universities. The flourishing of algebra in the medieval Islamic world and in Renaissance Europe was an outgrowth of the enormous simplification of computation through decimal notation. Various types of tools exist to assist in numeric calculations. Examples include slide rules and nomographs in addition to the electrical calculator. Arithmetic operations. The basic arithmetic operations are addition, subtraction, multiplication and division, although this subject also includes more advanced operations, such as manipulations of percentages, square roots, exponentiation, and logarithmic functions. Arithmetic is performed according to an order of operations. Any set of objects upon which all 4 arithmetic operations can be performed, and where these 4 operations obey the usual laws, is called a field. Addition is the basic operation of arithmetic. In its simplest form, addition combines 2 numbers, the addends or terms, into a single number, the sum of the numbers. Adding more than 2 numbers can be viewed as repeated addition. This procedure is known as summation and includes ways to add infinitely many numbers in an infinite series. Repeated addition of the number 1 is the most basic form of counting. Addition is commutative and associative, so the order the terms are added in does not matter. The identity element of addition is 0, that is, adding 0 to any number yields that same number. Also, the inverse element of addition is the opposite of any number, that is, adding the opposite of any number to the number itself yields the additive identity. For example, the opposite of 7 is -7, so 7 plus equals 0. Addition can be given geometrically as in the following example. If we have 2 sticks of lengths 2 and 5, then if we place the sticks one after the other, the length of the stick thus formed is 2 plus 5 equals 7. Subtraction is the inverse of addition. Subtraction finds the difference between 2 numbers, the minuend minus the subtrahend. If the minuend is larger than the subtrahend, the difference is positive. If the minuend is smaller than the subtrahend, the difference is negative. If they are equal, the difference is 0. Subtraction is neither commutative nor associative. For that reason, it is often helpful to look at subtraction as addition of the minuend and the opposite of the subtrahend, that is a minus b equals a plus. When written as a sum, all the properties of addition hold. There are several methods for calculating results, some of which are particularly advantageous to machine calculation. For example, digital computers employ the method of 2's complement. Of great importance is the counting up method, by which change is made. Suppose an amount P is given to pay the required amount Q, with P greater than Q. Rather than performing the subtraction P minus Q and counting out that amount in change, money is counted out starting at Q and continuing until reaching P. Although the amount counted out must equal the result of the subtraction P minus Q, the subtraction was never really done and the value of P minus Q might still be unknown to the change maker. Multiplication. Multiplication is the second basic operation of arithmetic. Multiplication also combines two numbers into a single number, the product. The two original numbers are called the multiplier and the multiplicand, sometimes both simply called factors. Multiplication may be viewed as a scaling operation. If the numbers are imagined as lying in a line, multiplication by a number, say x, greater than 1 is the same as stretching everything away from 0 uniformly, in such a way that the number 1 itself is stretched to where x was. Similarly, multiplying by a number less than 1 can be imagined as squeezing towards 0. Multiplication is commutative and associative, further it is distributive over addition and subtraction. The multiplicative identity is 1, that is, multiplying any number by 1 yields that same number. Also, the multiplicative inverse is the reciprocal of any number, that is, multiplying the reciprocal of any number by the number itself yields the multiplicative identity. The product of A and B is written as A times B or AB. When A or B are expressions not written simply with digits, it is also written by simple juxtaposition, AB. In computer, programming languages and software packages in which one can only use characters normally found on a keyboard, it is often written with an asterisk. *B. Division. Division is essentially the inverse of multiplication. Division finds the quotient of two numbers, the dividend divided by the divisor. Any dividend divided by 0 is undefined. For distinct positive numbers, if the dividend is larger than the divisor, the quotient is greater than 1, otherwise it is less than 1. The quotient multiplied by the divisor always yields the dividend. Division is neither commutative nor associative. As it is helpful to look at subtraction as addition, it is helpful to look at division as multiplication of the dividend times the reciprocal of the divisor, that is A divided by B equals A times 1. B. When written as a product, it obeys all the properties of multiplication. Decimal arithmetic. Decimal representation refers exclusively, in common use, to the written numeral system employing Arabic numerals as the digits for a radix 10 positional notation. However, any numeral system based on powers of 10, e.g., Greek, Cyrillic, Roman, or Chinese numerals may conceptually be described as decimal notation or decimal representation. Modern methods for four fundamental operations were first devised by Brahmagupta of India. This was known during medieval Europe as modus Indiarum, or method of the Indians. Positional notation refers to the representation or encoding of numbers using the same symbol for the different orders of magnitude and, with a radix point, using those same symbols to represent fractions. For example, 507.36 denotes 500s, plus 0 tens, plus 7 units, plus 3 tenths, plus 6 hundredths. The concept of 0 as a number comparable to the other basic digits is essential to this notation, as is the concept of 0's use as a placeholder, and as is the definition of multiplication and addition with 0. The use of 0 as a placeholder and, therefore, the use of a positional notation is first attested to in the Jain text from India entitled The Lock of Abhaga. dated 458 AD, and it was only in the early 13th century that these concepts, transmitted via the scholarship of the Arabic world, were introduced into Europe by Fibonacci using the Hindu-Arabic numeral system. Algorithm comprises all of the rules for performing arithmetic computations using this type of written numeral. For example, addition produces the sum of two arbitrary numbers. The result is calculated by the repeated addition of single digits from each number that occupies the same position, proceeding from right to left. An addition table with 10 rows and 10 columns displays all possible values for each sum. If an individual sum exceeds the value 9, the result is represented with 2 digits. The rightmost digit is the value for the current position, and the result for the subsequent addition of the digits to the left increases by the value of the second digit, which is always 1. This adjustment is termed a carry of the value 1. The process for multiplying two arbitrary numbers is similar to the process for addition. A multiplication table with 10 rows and 10 columns lists the results for each pair of digits. If an individual product of a pair of digits exceeds 9, the carry adjustment increases the result of any subsequent multiplication from digits to the left by a value equal to the second digit, which is any value from 1 to 8. Additional steps define the final result. Similar techniques exist for subtraction and division. The creation of a correct process for multiplication relies on the relationship between values of adjacent digits. The value for any single digit in a numeral depends on its position. Also, each position to the left represents a value 10 times larger than the position to the right. In mathematical terms, the exponent for the radix of 10 increases by 1 or decreases by 1. Therefore, the value for any arbitrary digit is multiplied by a value of the form 10n with integer n. The list of values corresponding to all possible positions for a single digit is written as 102, 10, 1, 10-1, 10-2. Repeated multiplication of any value in this list by 10 produces another value in the list. In mathematical terminology, this characteristic is defined as closure, and the previous list is described as closed under multiplication. It is the basis for correctly finding the results of multiplication using the previous technique. This outcome is one example of the uses of number theory. Compound unit arithmetic. Compound unit arithmetic is the application of arithmetic operations to mixed radix quantities such as feet and inches, gallons and pints, pounds, shillings and pence, and so on. Prior to the use of decimal-based systems of money and units of measure, the use of compound unit arithmetic formed a significant part of commerce and industry. Basic arithmetic operations. The techniques used for compound unit arithmetic were developed over many centuries and are well documented in many textbooks in many different languages. In addition to the basic arithmetic functions encountered in decimal arithmetic, compound unit arithmetic employs 3 more functions. Reduction, where a compound quantity is reduced to a single quantity, for example conversion of a distance expressed in yards, feet and inches to one expressed in inches. Expansion, the inverse function to reduction, is the conversion of a quantity that is expressed as a single unit of measure to a compound unit, such as expanding 24 ounces to 1 pound, 8 ounces. Normalization is the conversion of a set of compound units to a standard form, for example rewriting 1 foot 13 in as 2 feet 1 in. Knowledge of the relationship between the various units of measure, their multiples and their submultiples forms an essential part of compound unit arithmetic. Principles of compound unit arithmetic. There are 2 basic approaches to compound unit arithmetic. Reduction expansion method, where all the compound unit variables are reduced to single unit variables, the calculation performed and the result expanded back to compound units. This approach is suited for automated calculations. A typical example is the handling of time by Microsoft Excel, where all time intervals are processed internally as days and decimal fractions of a day. Ongoing normalization method, in which each unit is treated separately and the problem is continuously normalized as the solution develops. This approach, which is widely described in classical texts, is best suited for manual calculations. An example of the ongoing normalization method as applied to addition is shown below. The addition operation is carried out from right to left. In this case, pence are processed first, then shillings followed by pounds. The numbers below the answer line are intermediate results. The total in the pence column is 25. Since there are 12 pennies in a shilling, 25 is divided by 12 to give 2 with a remainder of 1. The value 1 is then written to the answer row and the value 2 carried forward to the shillings column. This operation is repeated using the values in the shillings column, with the additional step of adding the value that was carried forward from the pennies column. The intermediate total is divided by 20 as there are 20 shillings in a pound. The pound column is then processed, but as pounds are the largest unit that is being considered, no values are carried forward from the pounds column. It should be noted that for the sake of simplicity, the example chosen did not have farthings. Operations in practice. During the 19th and 20th centuries, various aids were developed to aid the manipulation of compound units, particularly in commercial applications. The most common aids were mechanical tills, which were adapted in countries such as the United Kingdom to accommodate pounds, shillings, pennies and farthings, and ready reckoners, books aimed at traders that catalogued the results of various routine calculations such as the percentages or multiples of various sums of money. One typical booklet that ran to 150 pages tabulated multiples from 1 to 10,000 at the various prices from 1 farthing to 1 pound. The cumbersome nature of compound unit arithmetic has been recognized for many years. In 1586, the Flemish mathematician Simon Steven published a small pamphlet called De Thiende, in which he declared that the universal introduction of decimal, coinage, measures, and weights to be merely a question of time, while in the modern era, many conversion programs, such as that embedded in the calculator supplied as a standard part of the Microsoft Windows 7 operating system, display compound units in a reduced decimal format rather than using an expanded format.